So good morning to everyone. So in the last video we have discussed about the types of constrained motions and types of kinematic pairs and kinematic chain. Is it a kinematic chain or not? You can check by using the formulas. Okay, now we are going to discuss in this video types of joints in a chain. So what are the different types of joints in a chain that we are going to discuss? So different joints are there. First one is binary joint. Binary nothing but 2 points. So then two joints, binary joint nothing but two elements joined at the same connection. Then the joint is known as binary joint. So the figure you can observe 4 joints. Okay, 4 binary joints at A, B, C, D. In order to determine the nature of chain, whether the chain is a locked chain or kinematic chain or unconstrained chain, the following relation between the number of links and number of binary joints as given by A.W. Klein may be used. Okay, that is called as Klein equation. Now J plus H by 2 is equal to 3 by 2 L minus 2, where J is the number of joints, H is the number of higher pairs, L is the number of links. Now from this figure you can observe this higher pairs is 0, then you can substitute H value 0. Okay, in this case H is 0. By substituting H is 0, the equation will become similar to previous equation, that is JB is equal to 3 by 2 L minus 2. So from this, substituting the values binary joints, applying the equation to a chain, L is 4, J is 4, and this will be both are equal, therefore it is a constrained kinematic chain. Kinematic chain or constrained chain. Okay, similarly ternary joint, second one, when there are 3 links are joined at the same connection, the joint is known as ternary joint. 3 links are joined at one connection, then it is called as ternary joint. It is equivalent to 2 binary joints, as one of the 3 links joined carries a pin for the other 2 links. Now this is the figure you are observing. Ternary joints at C and E. A, B, D are the binary joints. C and E are the ternary joints because 3 links are joined at the points C and E. So from this, total number of joints will be equivalent to that binary joints is 3 binary joints and 2 ternary joints. Each ternary joint is equivalent to 2 binary joints. Therefore 3 plus 2 into 2, total number of joints is 7. Now determine whether chain is a kinematic chain or not. So for this, you know that links is 6, joints is 7. Therefore from equation J is equal to 3 by 2 L minus 2, 7 equal to 7. Therefore it is a kinematic chain, okay, or constrained chain. So left hand side values are equal to the right hand side value. Therefore it is a kinematic chain or constrained chain. Next one is quaternary joint. When 4 links are joined at the same time connection, then the joint is called a quaternary joint. 4 links are joined at one point, then the joint is called as quaternary joint. It is equivalent to 3 binary joints. So one quaternary joint equivalent to 3 binary joints. In general, L is the number of links are joined at the same connection. The joint is equivalent to the L minus 1 number of binary joints. L minus 1 binary joints. So consider the chain having 11 links in this figure. Next figure I will show the figure. At one binary joint at D, 4 ternary joints at A, B, E and F, and 2 quaternary joints C and G. Since one quaternary joint is equivalent to 3 binary joints and one ternary joint is equivalent to 2 binary joints, therefore total number of joints in a chain as shown in figure are calculated like this. So we are observing, so quaternary joint, ternary joints are in this point. D is the only binary joint and B, A and B, A, E are the ternary joints. C also ternary joint, and F and G are the FC. F is also ternary joint, 3 points, and G and C are the quaternary joints. So now from this condition we are substituting 1 plus 4 into 2 plus 2 into 3. So 2 quaternary joints, 2 into 3, 4 by ternary joints, 4 into 2, and 1 binary joint, total 15. So next coming to the second figure you are observing. So in this figure we can see that 1 is the binary joint at D and 6 are the ternary joints. Therefore 6 into 2, total 13 binary joints are having equivalent to this second figure. Now determine figure A is kinematic chain or not. For that, number of links is 11, J is 15, and then we know substituting the values in this equation. Left hand side value is greater than its right hand side value, therefore it is not a kinematic chain, it is a locked chain. Left hand side value greater than the right hand side value, then it is called as a locked chain and forms a rigid frame or structure. Okay, next coming to the second one. So figure B, you observed, so that is a 6 ternary joints at A, B, C and F and G. Therefore total number of joints is equivalent to that binary joints are 13. Substituting this value, so number of links is 10 and joints is 13. Substituting the values both are equal, it will become a kinematic chain or constrained chain. Next one is I have to discuss about. So till now we have discussed about the types of joints. Now we are going to define the mechanism. Mechanism nothing but when one of the link of kinematic chain is fixed, the chain is known as mechanism. So when the kinematic chain in one link is fixed, then it is called as a mechanism. It may be used for transmitting or transforming motion. Mechanism is used to transmitting or transforming the motion. Example, engine indicator, typewriter are the examples, and watch, mechanical watch is also one of the example for mechanism. A mechanism has with 4 links is known as simple mechanism. So if it is only any mechanism having only 4 links, then it is called as simple mechanism, and the mechanism with more than 4 links is known as compound mechanism. More than 4 links, then it is called as compound mechanism. Mechanism is required to transmit power or to do some particular type of work. It then becomes a machine. So machine means it is doing some work, then it is called as a machine. Mechanism is required to transmit power or to do some work, then it becomes a machine. In such cases, the various links or elements have to be designed to withstand the forces, that is both static and kinetic, safely. Okay, therefore for any machine or mechanism, forces will be transmitted, therefore you have to design to withstand these forces. Now a mechanism may be recorded as a machine in which each part is reduced to the simplest form to transmit the required motion. Mechanism, each part is reduced to the simplest form to transmit the motion. Now number of degrees of freedom for plane mechanisms. So this is called as movability. So movability of plane mechanisms we will discuss now. Number of degrees of freedom for plane mechanism. So this is in this design or analysis of mechanism, one of the most important concern is number of degrees of freedom, or also called movability of the mechanism. Movability of the mechanism is one of the important parameter which design whenever you want to design a mechanism. So therefore number of input parameters, whatever the number of input parameters, usually pair variables which must be independently controlled in order to bring the mechanism into useful engineering purpose, then that number of input parameters are called as number of degrees of freedom. So number of input parameters which must be independently controlled in order to bring the mechanism into useful engineering purpose or to become a machine. So it is possible to determine the number of degrees of freedom of a mechanism directly from the number of links and number and types of joints. Number and types of joints. So number of links and number and types of joints is useful to calculate the number of degrees of freedom. Now we are considering a 4-bar chain. A little consideration will show that only one variable such as theta is needed to define the relative position of all the links. In other words, we say that number of degrees of freedom is 1 of a 4-bar chain is 1. So now 4-bar chain and 5-bar chain, I will show the figures in the next slide. So 5-bar chain also shown in figure. So in this case 2 variables are needed to define completely the relative position of all the links. Thus we say that number of degrees of freedom is 2. If it is number of degrees of freedom is 1, it will get completely constrained motion will get. Okay, first figure you are observing 4-bar chain. So only theta is sufficient to define the all link positions, whereas in the 5-bar chain theta 1 and theta 2 is required to define all the links position. So that's why number of degrees of freedom for the first figure is 1, second figure is 2. So now in order to develop the relationship in general, two links AB and CD in a plane motion as shown in figure, we are observing the link will AB with coordinate system OXY is taken as the reference link or fixed link. The position of point P on the moving link CD can be completely specified by the three variables, that is the coordinate of the point P denoted by x and y, and the inclination of the link CD with x-axis of the link AB. So that is one link have to be defined. So three parameters are required whenever independently keeping. Whenever you are joining these two links, CD is joined to AB, then only one parameter is sufficient, theta. So therefore two parameters are reduced whenever joining by these two links. Therefore number of degrees of freedom, whenever it is individually it is there, so number of degrees of freedom are 3. Whenever it is connected to fixed link, it will become number of degrees of freedom is 1. That means two parameters or 2 degrees of freedom is reduced. So such that each link of a mechanism has 3 degrees of freedom before it is connected to any other link. When it is connected to the link by a turning pair, the position of the link CD is now determined by a single variable. Already I told you. So now when link is connected to a fixed link by turning pair, 2 degrees of freedom are destroyed. So 2 degrees of freedom are destroyed, therefore only 1 degree of freedom we are getting. So this may be clearly understood from figure, in which the resulting 4-bar mechanism has 1 degree of freedom. So such that, so we are observing, so single mechanism we are observing, all are different, they are not connected, even one link. 4 links are individually, then one link is fixed, so remaining 3 links positions are 3 into 3, total 9 degrees of freedom are there with respect to first link. Similarly, whenever one link is connected, second link or third link is connected, one link is connected, then remaining are 7 are the degrees of freedom. 2 links are joined, only 5 degrees of freedom. So 3 links are joined, then we got it number of degrees of freedom 3, and all links are joined, then number of degrees of freedom becomes 1. So that's the way 4 bar chain, number of degrees of freedom will becomes 1. Now consider a plane mechanism with L number of links. Then since in a mechanism one of the link is to be fixed, therefore the number of movable links will be L minus 1, and thus the total number of degrees of freedom will be 3 into L minus 1 before they are connected to any other link. So therefore whenever you are connected, then they will be reduced to number of joints. Therefore in general mechanism, L number of links are connected by J number of joints or lower pairs, and H number of higher pairs. Then the number of degrees of freedom for if mechanism is given by the equation n is equal to 3 into L minus 1 minus 2J minus H. So this is the equation we are called as Kuchbach criteria for the movability of a mechanism. So this equation is called as Kuchbach criteria for the movability of a mechanism having plane motion. So n equal to 3 into L minus 1 minus 2J minus H is the Kuchbach criteria. Whenever H is 0, higher pairs are 0, no higher pairs, then H will becomes 0. Therefore n equal to 3 into L minus 1 minus 2J will be the equation. This is equation, we got it. So from this condition we can say that applications of Kuchbach criteria of two plane mechanisms. So first one, 3-bar mechanism, 4-bar mechanism, 5-bar mechanism, 5-bar mechanism and separately 6-bar mechanism. So these are the different mechanisms. So for these mechanisms we are applying Kuchbach criteria. Then how many number of degrees of freedom we are having, we can check it. So first one, n is equal to 3 number of links. 3 number of links are there. So number of joints is also 3. So substituting higher pairs is 0. So then 3 into L minus 1 minus 2J. So the number of degrees of freedom will becomes 0. 6 minus 6, G becomes 0. So first one, it is 0. H is 0. Therefore we are substituting the first equation, 3-bar chain, number of degrees of freedom will be 0. So second one, we are observing 4 links are there, 4 joints are there. Substituting in this equation, higher pairs is 0. Then 3 into 4 minus 1 minus 2 into 4, that is 3 into 3, 9 minus 2 into 4, 8. 9 minus 8 is 1. So therefore 1 degree of freedom we got it in the 4 bar chain. 4 bar mechanism, 1 degree of freedom. So next figure C, you are observing 5 bar mechanism. So in this case also, so number of links is 5, number of joints is 5. Okay, then substituting the equation, higher pair is H is 0, then so this will become 3 into 5 minus 1, so that is 12, minus 2 into 5, 10. So therefore it becomes number of degrees of freedom is 2 for a 5 bar mechanism in figure C. In the figure D, you are observing number of joints is only 4, then the number of links are 5. So therefore for this figure n is equal to 3 into L minus 1 minus 2j, H is 0, therefore 3 into 5 minus 1, that is 12, minus 2 into 4, 8. So 4 degrees of freedom will be the number of degrees of freedom will be the 4. Number of joints is only 4, number of links are 5. Okay, so now similarly 6 bar mechanism you are observing, so 6 links and number of joints is only 4. Okay, so 4, but one thing, actually previous case also 5 bar mechanism is also figure D is not number of joints is not 4, because 2 are the ternary joints, A and C are the ternary joints, therefore 4 equivalent binary joints, 4 plus 2 6. So that is the number of joints. 6 means, so 3 into 5 minus 1, that is 12, minus 2 into 6, 12, 0. So therefore degrees of freedom will be the 0 for 5 bar mechanism for the figure D. Figure E also similar way. So 3 ternary links, 4 joints are ternary joints, therefore 4 into 2, 8 number of binary joints, so 8 into 2, 16, and links are 6, so 15 minus 16, it will becomes negative, minus 1. Okay, number of degrees of freedom will be minus 1, so that should not be taken as minus 1, this will be taken as a positive value. Okay, consider that will be seen later. Now we are observing figure 3, first one figure A, so number of degrees of freedom 0, second figure B, number of degrees of freedom 1, so third one number of degrees of freedom is 2, fourth one number of degrees of freedom is 0, fifth one is minus 1, already calculated, I already mentioned that. The next one is when n is 0, the mechanism forms a structure and no relative motion between the links is possible. So that is figure A and D are the structures, there is no kinematic chain, these two. And when n is 0, it is called as a kinematic chain. When n is 1, the mechanism can be driven by a single input motion. Okay, when n is 2, two separate input motions are necessary to produce constrained motion for the mechanism. Similarly, when n is minus 1 or less, then there are redundant constraints in the chain and it forms a statistically indeterminate structure. So this is called as indeterminate structure when number of degrees of freedom is minus 1 or minus in terms of negative values. So we can say it is indeterminate structure. So the application of Kurzweil criteria applied mechanisms with higher pairs or 2 degrees of freedom joints as shown in figure. Then in figure A there are 3 links, 2 binary joints and 1 higher pair, then H is 1, then substituting the values n is 1. So then in figure B also substituting 3 binary joints and 1 higher pair, then L is 4, J is 3 and H is 1, number of degrees of freedom is 2. Here it has been assumed that so slipping is possible between the links, that is between the wheel and fixed link. However, if the friction at the contact is high enough to prevent slipping, the joint will be counted as 1 degree of freedom pair because only one relative motion will be possible between the links. So this is the way your observed figure mechanism with higher pair of first one 2 and 3 forms higher pair, and similarly here 4 and 1 forms the higher pair. So that is the way. So you are observed. Now Grubler's criteria, Kurzweil's criteria is over. That is Kurzweil's criteria is 3 n equal to 3 into L minus 1 minus 2j minus h. Now Grubler's criteria for plane mechanisms nothing but, so in this case only thing is single degree of freedom joints with single degree of freedom joints when the overall mobility of the mechanism is unity. So whenever n is 1, mobility is 1. So then that equation you can call as substituting n is 1 and h is 0 for the in Kurzbach equation. Then so n is 1, 3 into L minus 1 minus 2j, okay, h is 0. So our 3 into 3L minus 2j minus 4 is 0. Okay, this is the equation. This is called as Grubler's criteria for the plane mechanism with constrained motion when h is 0 and n is 1. Okay, this is the Grubler's criteria. 3L minus 2j minus 4 is 0. Okay, now for a plane mechanism with mobility 1 single degree of freedom, joints cannot have odd number of links. The simplest possible mechanism of this type of is a 4-bar mechanism and a slider crank mechanism in which L is 4 and J is 4. Okay, simplest mechanism is 4-bar mechanism and slider mechanism, so where number of links are 4 and number of joints is also 4. So in this way we can classify the mechanism. Now in the next video we are going to discuss about various mechanisms, 4-bar chain, then single thread crank chain, then inversions of 4-bar chain and single thread crank inversions of single and double crank slider crank chains will be discussed in the later videos. Thank you.